So we've spent some time talking about functional limits and then use the definition of a functional limit to carefully define what we mean by a continuous function. And we spent some time proving that functions that we have kind of understood to be continuous for a while now, we spent some time proving that those functions are in fact continuous using the definition. And we're going to extend that now a little bit to a concept that is probably not as familiar as just plain continuity, and that's the idea of uniform continuity. And we're going to introduce that new idea by taking a look at two examples where we are going to show that a function is continuous, but in the end we'll sort of highlight that there's an important difference between the ways in which they are continuous. So I've done a lot of the sort of algebra work beforehand, but let's step through the first example. So we have here a linear function, f of x is equal to 3x minus 4, and we want to show that f is continuous for any point c. So x can be anything. We're going to fix the point though and call it c. And we start this the way we start all such problems. Let epsilon be bigger than 0. Consider the thing that needs to be made small. That's f of x minus f of c. So here's f of x, 3x minus 4. Here's f of c, 3c minus 4. And we do a little bit of algebra inside the absolute values. And we end up with the expression 3 times the absolute value of x minus c. That's where we reveal the delta, because we know what we have control over is how close x gets to c. So 3 times x minus c is less than epsilon. This is what we want to have happen. Whenever x minus c in absolute value is less than epsilon over 3, and that reveals the choice of delta. Our delta sub epsilon will be 1/3 epsilon. And note that this works for any point c. Okay, we started with some point x equals c, we went through the proof, and it turned out that the c didn't matter in the choice of delta. And that's going to be important. So let's contrast that with the second example, where we're going to show that the function g of x, which is going to be x cubed, that's going to be continuous at any point x equals c, and we're going to use the definition of continuity to show that. This one's a little harder algebraically, and it involves a two-stage delta, and we've seen that before, but I've kind of left it at the point where we need to start doing those things. All right, so I've got the absolute value of the thing that I want to make small, that I need to make less than epsilon. That's x cubed minus c cubed. And if I just factor using the difference of two cubes, then I can pull the x minus c out, and what I'm left with is x squared plus xc plus c squared. Now, again, this is kind of typical for this kind of argument, but we crash through here with the triangle inequality, and that allows us to write something that we know to be at least as big as the original, and that is absolute x squared, absolute x times absolute c, and plus absolute c squared. Right, so we've used the triangle inequality there twice. Now, we want to make this last expression less than epsilon, but the sticking point is this expression here. And we have to produce a bound for that, so then we know how small to make x minus c. So let's take my delta 1 equal to 1. Then if x minus c is less than 1, that implies that absolute x is less than absolute c plus 1. And then I can replace all of the x's in this term I need to bound with this upper bound absolute c plus 1. So I end up with I have x minus c times x squared xc c squared. That's less than, or sorry, strictly less than x minus c. And then absolute c plus 1 squared plus absolute c plus 1 times absolute c plus absolute c squared. All right, now inside these parentheses, the large bounded term, I can simplify, collect like terms, and then I'll have that that's equal to x minus c, and what the result is 3c squared plus 3c plus 1. All right, well, now we have something that doesn't depend on x, and I can make that less than epsilon. And that happens whenever x minus c is less than epsilon divided by 3 absolute c squared, 3 absolute c plus 1. And then if I was going to finish the proof off formally, what I would do is take my delta to be the minimum of delta 1 and this delta 2. So if this is delta 2, then my final delta would be the minimum delta 1 and delta 2. Now, we don't have to worry about finishing up this proof formally. What's important is that the delta that we find here at the end is different than the way the delta works out in the end for the first example. And the important difference is that this delta for the function x cubed relies on the actual point c, right? It depends on which point you started with as to how small delta has to be. So, for example, if we were investigating the point c equals 0, then this delta 2 would be, well, 0 plus 0 plus 1, so it would just be epsilon. But if c were 10, then I'd have to take a much smaller delta because this c squared would be 100, so I'd get 300 plus 30 plus 1, so roughly epsilon over 331. And you can see for a really big c like a trillion, delta has to be really, really, really small compared to the epsilon. So we have two functions, both are continuous. One has a delta that works for every c at the same time. The other has a delta that works for every c, but each delta depends on the c. So this is going to turn out to be an important difference. And with a definition that we'll see in the next video, we're going to call a function like f of x, 3x minus 4, that's going to be considered to be uniformly continuous, in that it doesn't matter which c you start with, you can pick the same delta. All right, so that's uniform continuity. G, on the other hand, will not be uniformly continuous over R anyway, because there is no single delta that works for every c. Right? Here the delta depends on the c, so G will be continuous on the reals, but it won't be uniformly continuous because the delta depends on the point of interest. All right, so we'll take a look at the formal definition of uniform continuity next, and then take a look at a couple of examples.